Okay, good morning. We are on lecture 17, right? Any general questions? How did the X-foil assignment go? It was due Sunday, right? Yeah, did it? Any big troubles? Okay. I'm going to take a little detour and talk about homework 3, which I need to assign like today after class. This homework used to have 3 problems, but because of the switch in the topics and because I want to get to this part, I want to give less time for this homework and get to profile quickly. I'm going to eliminate the first 2 questions. So let's talk about the third question, which is the big important part of homework 3. I'll post this, it's not yet there, but for now let's just talk about it. Okay. So this is a homework where you're going to use X-foil to design a fairing. And a fairing is something like this. Suppose you have some structure that's in the fluid, it's exposed to the fluid flow, so this is V infinity. This is going to cause a lot of drag, and obviously to reduce drag what you can do is you can put a fairing around it. Right? Fairing is just an airfoil streamlined shape that goes around the bluff body. And this is just some random shape. It could be a flat plate, it could be a cylinder, something like that. So your task in this problem is to design a fairing, and the height of the fairing, the height of this object is 2.5 centimeters, and you can assume that this is exposed to sea level atmosphere with this density, air density and kinematic viscosity. And you're going to start off with a baseline airfoil that I'm going to give. It's a 10% thick airfoil, and you're going to use X-foil to calculate what the resulting drag is going to be, drag per unit span. So because we are doing this in 2D, the drag will depend on the span, right? So we'll take a meter span and say what is the drag of that meter span of the wing or of the fairing. We're not going to consider 3D effects. It's just an airfoil problem. Drag per unit span in newtons per meter. But just because there is an airfoil given to you doesn't mean it is the best airfoil, right? So who's to say that if we take this fairing and lengthen it, the drag won't decrease? And who's to say, I mean, we don't know the answer. It could be that this is too long. Maybe you should have a shorter fairing, right? So that's kind of the design problem, if we call it that. To sort of get used to this, we are going to reduce the thickness, maximum thickness of the airfoil. Instead of 10%, you're going to reduce it to 9%, which you can do with X-foil itself. You can do GDES, T-set, and exec. I think it's T-set. This command changed, so it might be T-set or T-cam. Anyway, then you redistribute and make sure it has 200 panels, and determine the drag per unit span again. For the new airfoil, but remember that of course the chord is going to change. If you use a 9% thick airfoil, you'll have a different chord. If the chord changes, Reynolds number will change. And did you find the drag again? So that will start telling you which direction you have to go, right? If 9% airfoil is going to have less drag than the 10% airfoil, the physical thickness is the same. It's 9. When I say 9%, the chord changes. So if the 9% is less, that means you can go even lower and lower. Or if the 9% is higher, that means you have to go to a higher T over C ratio. So you determine the optimum T over C max for minimum drag, which is not necessarily minimum CD. Okay, so this is a confusing thing, and I mean, there are two or three ways of doing this problem, and depending on how you do it, it's not necessarily the minimum CD. So, so you create a table of different T over C max and the total drag, and make a plot and find the best T over C max. But that is not always universal. That depends on the flight speed. So we did this for 60 meters per second. If you go to 30 meters per second as the velocity, then your answer might be different. So repeat the whole problem for 30 meters per second. And so this will help you kind of put together some of the things we have learned before, and also talk about thickness to chord ratio and Reynolds number effects and so on. So let's kind of talk a little bit more about this problem. So homework 3, fairing design, right? Max thickness, physical thickness is 2.5 centimeters. And you have a fairing like this. This is the chord. So if T over C max equals 10%, what is the chord? So obviously you would put this fairing at the maximum thickness location, right? You wouldn't put the fairing here, or you wouldn't size the airfoil so that this bluff body is here. You'd put it at the maximum thickness. That will make it you'll avoid unnecessary thickness. So what's the chord if T over C max is 10%? 25 centimeters, right? Does it make sense? So this is 2.5 centimeters. So the chord is 25 centimeters. And can you calculate Reynolds number for me? Given that density is 1.23 kilogram per meter cubed, new kinematic viscosity is 1.46 times 10 to the power minus 5 in SI units. Remember the expression for Reynolds number? VC over nu, or if you include density in the top, this will become mu, right? It then will become dynamic viscosity. We're talking about kinematic viscosity. So anybody got the answer? Velocity is 60 meters per second. Okay, it's probably, that's what somebody else getting? You're getting this 1.0703 something, so something close, right? Remember to convert this to meters. Okay, so How will you do this in Xfoil? So suppose I give you the airfoil coordinates, and I'm going to call that baseline .dat. So the airfoil coordinates will be like x going from 10 to 00 to 10, right? Usual set of coordinates. So can you tell me what the steps are, just approximately? What will you do? You load this airfoil in Xfoil, and then you'll set the, you'll make it 200 points, do PPAR and do the 200 points. Then you go to Opera menu, and then you set the Reynolds number, and you run it at what angle? 0, right? We are only talking about 0 degrees. So alpha 0, and you will get a CD. You have put the Reynolds number. So okay, so it will give you the CD. What can you do to get drag? So you run Xfoil. At RE 1.03 million, alpha equals 0, get CD. So can drag per unit span is? Yeah, so half rho V infinity squared. V infinity is 60, rho is 1.23. CD, and then length scale, right? So you need the C, and the C is 0.25. So 25 centimeters is 0.25 meters, right? So this will turn out to be some number. That is your drag. Now the second part of this question is, now reduce thickness to 9% chord. So what do? You load the baseline airfoil. That part is the same. Pardon me? Yeah. So load airfoil into Xfoil. Do you'll have to do T-set, exec, and all that stuff. Okay, now you have an airfoil that's set to 9% chord after you do come out of this. Now you go and run it at alpha equals 0. And what Reynolds number? What is the chord? The chord was 0.25 only for T over C of 10%, right? Now you have a different chord. So this height is the same. And earlier we had this airfoil. Earlier we had a chord of 0.25. So now you have a thinner airfoil, thinner meaning T over C is smaller, but the thickness itself is the same. So chord is what? 27.8, okay. So it'll look like this, something like this. You have a more higher fineness ratio fairing. Point 278, 27.8, is it? Something like that, okay? I'm not doing the calculations now. So this is 9% thick. And this was the earlier one, 10% thick. What else will change? Chord is now different. Check it, because I'm just putting down some numbers for the sake of discussion. And then Reynolds number will change. Reynolds number is VC over nu. So that will be whatever it is with the new chord. And so that's the Reynolds number you have to run it at. And now you'll get a CD. Now calculate drag per unit span. So here you have to use the new CD and the new chord. Okay, so now you will get a new drag per unit span. Maybe it will be less, maybe it will be more, but that will tell you which way to drive the airfoil, T over C max. And then so there will be a point, usually there will be a point at which there will be a best T over C, after which, on both sides of which drag will increase. So that's the optimum thickness to chord ratio. That will tell you whether the fairing should be long or whether it should be short. And all of that will depend on the velocity. So you do this for 60 and then you repeat it for 30 and see how the results look. So this all seems straightforward, right? The reason this may cause confusion is X-foil has some built-in capability to vary the chord, and so I'm actually hesitant to even talk about this option because it is a nice option, but right now, if you have understood this and I tell you the other method, you may get confused. Usually about 1/3 of the class messes this homework up. Okay, so it's like this. There are two methods, right? There's method 1, there's method 2. If you do method 1 all just by that, continue to use method 1 throughout, then you'll be fine. Or you can continue to do method 2, but do method 2 only, and then you'll be fine. The problem comes when you misunderstand these things and do some kind of a half of method 1 combined with half of method 2, then you'll mess the problem up. So I'm going to say this, and then if you get confused, I'm not going to be responsible. Okay, so let's talk about an alternative method. You don't have to do this. So if this is not intuitive to you, just leave it alone and do it the other way. So in this method, so you can you can, when you put it in X-foil, right, in X-foil, let's say this is a 10% thick airfoil. So this will go from 0 to 1. So chord C in X-foil equals 1. That's how we did the previous time too, right? Chord inside X-foil, chord is 1, and T over C max is this is 0.1. So this is a 10% airfoil. So X-foil actually RE is really set for C X-foil, and CD is let's say RE is set for C X-foil equals 1 and CD is based on C X-foil equals 1. So so that's why it's actually in X-foil they write this as capital R capital E to remind you that this is really V times 1 over nu, and CD so in other words, if you set RE is 1.03 million, this 1.03 million is taken as the Reynolds number for a unit chord in X-foil. So when you go to a 9% thick airfoil, you can actually you can go and increase the chord length inside X-foil so that the chord length becomes, what should it be 1.11? Can somebody do 1 over 0.09? Is it 1.11?
Yes.
Okay. So this is the 9% airfoil. And this CX foil here is 1.11. It's 1 over 0.09. So inside X foil, chord doesn't have to be 1. So you can actually go and say, reduce T over C to 9% and then increase the chord to 1.11. So, and then you're telling X-foil, go analyze this airfoil with a chord of 1.11, and if you do it that way, you don't have to change the Reynolds number, because X-foil defines this Reynolds number for a unit chord, and if the chord is 1.11, the airfoil Reynolds number, the aerodynamic Reynolds number will automatically become larger. But in X-foil, you're defining X-foil the Reynolds number as 1.03 million for a chord of 0 to 1, for a chord of 1. So by increasing the length, the Reynolds number is automatically changed even though you don't physically change the number. And CD is also, the CD that you get is proportional to D prime, because you've physically increased the chord in Xfoil by 11%. Okay, so there are some situations, and it's not necessarily restricted just to fairing design, where you can actually, inside Xfoil, you can quickly iterate and say, reduce thickness, increase chord length. You don't change Reynolds number, you just go and run it and see the CD. If the CD increases, that means you know drag is increasing. Okay, same thing, CL, that's why CL is also CL is also written for a unit chord. Okay, so you can do this approach, but this is a little bit more, you got to get your head successfully wrapped around this. Only then you will get this correct. So, and you don't have to. So if this is, it takes some time. You know, some people get this right away and they say, yeah, this makes sense, and others just find this pretty confusing. So if you don't understand this method, that's fine, don't do it. Just do it the usual way. Every time, make the chord equals 1, run it in Xfoil, change Reynolds number, and you have to calculate Reynolds number, put the correct Reynolds number, get the CD, and then calculate D prime using the actual chord. And then you have to keep doing that for every CD, every T over C value. And it's not hard, it's just you got to go through it. Or you do this option where you change the chord inside Xfoil. Remember, this is not the physical chord, right? The physical chord is 0.25 meters, but we call that as 1 in Xfoil. We call that as the baseline. So, or do this method. But what you really shouldn't do is mix up, do half of one method and half of another method, then it will be wrong. If you want to challenge yourself and kind of understand this nicely, then you do both methods and you'll get approximately the same answer. You know, there'll be some small difference because of just some rounding off and so on. Yes, you had a question, Ethan? Yeah, that should be L prime, correct. Now that would be really confusing, right? Okay, is that your question too? Okay. So this won't take long at all, but I recommend doing this, starting on it soon, because there is a potential that halfway through you'll get confused. Chances are you won't, everything will probably go fine, but if you do get confused, you need time to sort it out, so start early. And I'm going to give, I mean, this is just one problem. You can sit down and do it in like a couple of hours max. So I'm going to give until Tuesday next week, end of the day, in midnight on Tuesday. So you will have 2 more classes, lectures where you can clear. If you have some confusion, you can ask me. So Thursday and Tuesday you will have it. And after Tuesday, I'll give an assignment. It's really now the project 1, where you'll use Profoil, and you'll actually design a symmetric airfoil for a similar problem. So it's really important you do this homework before you do that project. So, spend some time on this. Like I said, it's not hard. It's just, there's a small chance that you might get confused, in which case you should give yourself time to sort it out. Okay, so any questions? Okay, let's move on to where we were with Profoil. So just as a review, in the last class we stopped somewhere here. We talked about how in Profoil you divide the airfoil into segments, and every segment except the first and the last segment, all other segments have this alpha star concept. And alpha star is the design angle of attack relative to zero lift angle for a segment, and CL star is the design CL for that segment, and CL star, as we know from thin airfoil theory, is going to be proportional to alpha star, so it will be 0.11 times alpha star when alpha star is in degrees. So the nice thing is, if you have an airfoil where some segment has some alpha star, and if you go and analyze that airfoil with alpha z, which is angle of attack relative to zero lift line or absolute angle of attack, if you set the absolute angle of attack equal to alpha star, then that segment will have zero velocity gradient. And as an example, we started talking about this. Here is a 4-segment airfoil, and so we have segment 1, 2, 3, 4, and remember we always use the end point of a segment for denoting the segment number. So this is really segment 2, and this is the end point of segment 2. So if this segment has an alpha star of 7 degrees, that means when you analyze this airfoil, you can analyze it in profile itself or in X-foil. When you analyze it at absolute angle of attack of absolute angle of attack of 7 degrees, which will give approximately CL of 0.77. Right? Then the velocity distribution over this segment will be flat. It will have a zero gradient. I think we talked about how this is actually very useful, because this demarcates anything greater than 7 degrees angle of attack. This velocity will have adverse pressure gradient, and that's what controls boundary layer behavior, right? Anything less than 7 degrees, it has favorable gradient. Now let's take the same airfoil and let's put some alpha star for the third segment. So we said alpha star equals 7 degrees for segment number 2. Now we'll go to segment number 3, and let's say alpha star is 3 degrees. It could be anything. I'm just using an illustration here. Alpha star for segment number 3, right? This is segment number 3. That means CL star for segment number 3 is 0.33. So just don't confuse the segment number and the alpha star. In this particular example, I just chose 3 degrees for segment number 3. It's just coincidence. Okay, so now if you run the velocity plot the velocity distribution, you generate the airfoil and then you go analyze it, and you plot the velocity distribution. It will turn out that the velocity distribution will be something like this. So the velocity distribution will be something like this. So this point, this x over c is this. So this is segment endpoint 1, this is segment endpoint 2, this is segment endpoint 3, and this is 4. So you see that the lower surface segment, the leading edge, in the front segment on the lower surface has got exactly 0 velocity gradient, and this is for alpha z equals 3 degrees or CL equals 0.33. So now the second segment will have some other, it will have whatever velocity distribution is needed to make it work. And so now you can achieve both of these simultaneously. You can say, I want this airfoil to have segment number 2 of alpha star of 7. That means at 7 degrees absolute angle of attack, that will have a flat velocity distribution. Simultaneously, at an alpha z of 3 degrees, I want the lower surface segment 3 to have a flat velocity distribution, and I want both of these, right? So if you run this same airfoil, if you run it at CL of 0.77, you'll have flat top here, and same airfoil, if you run it at 0.33, this will be flat. And these are at different angles of attack, so you're using different portions of the airfoil, one portion for one angle of attack, another portion for another angle of attack, and you get both. So the nice thing is, so segment 2 alpha star and segment 3 alpha star are satisfied. So that's why this is called multi-point inverse method. So multi-point because you're specifying velocity distributions or something about the velocity distribution at two different conditions. Inverse because you're not even saying what geometry you want. You're saying, I want this velocity distribution, figure out what the geometry is, and the method will go and figure it out. Just to complete this thought, the reason this is so cool is that at some angle of attack that is near 3 or near 7, you can say what will be the gradient of the velocity distribution. So if we take alpha z equals 7 degrees or CL equals 0.77, and if you look at the velocity distribution, it will look like this. Right, upper surface segment number 2 will have a flat top, a flat zero velocity gradient, and lower surface will be whatever it is. And if you go to slightly more than 7 degrees alpha, what will happen if you go to slightly more than 7 degrees alpha? What is the one thing you can say? Yeah, so this segment, instead of being flat, will have adverse gradient. So it will look like this, right? And then it will look like this. And the lower surface will be like this. Okay, now I'll use a thick red line to say what will happen if you have alpha z little less. What will happen if you have alpha z little less than 7 degrees? It will be favorable, right? So it will look something like this. So if this happens to be a Reynolds number where you need something like a flat zero velocity gradient to sustain laminar flow, then at CL of 0.77 you'll have laminar flow all the way till here. At a CL of little greater than 0.77, laminar flow will suddenly transition will move from here to here. So you're defining where the upper corner of the drag bucket is. Now simultaneously we are also telling Profoil what we want for the lower surface. So let's do that for alpha z equals 3 degrees, which is CL of 0.33, and that velocity distribution will look like this. The same airfoil will now have as we saw, a flat velocity distribution on the lower surface, and the upper surface will look something like this. And this is at CL of 0.33. If you go to a slightly higher angle of attack, what will happen?
Between
2 and 3. Really, this is really 2. It's 2 starts here. This is velocity of 1. So what will it be on this? So if you go to a higher angle of attack, like let's say 3.2, what will happen on this segment? Adverse? It will be favorable. Now remember, this is lower surface. So lower surface works the other way, right? So now at little higher angle of attack, let's say 3.1 or something, you will have something like this. And the upper surface will be something like this. So higher the angle of attack, the lower surface curves will move, down. Velocity distributions will get more favorable. So this is alpha z a little greater than 3 degrees. And a little lower angle of attack, now it will become adverse. This segment will become adverse. So you'll have it like this. And the effect on the polar, it will really depend on the Reynolds number, but you can quickly calibrate yourself by running an X-foil run or two for that Reynolds number. And the sort of trends you can do are like this. This is not always going to happen. Like I said, it will depend on Reynolds number, but for certain Reynolds numbers, you will end up with something like this. So the airfoil so around 0.3 and around 0.7, let's say, are our 2 points that we're going to look at. So approximately you will have if this is a natural laminar flow airfoil, you will have a bucket or drag behavior, something like this. Because this was around 0.77, so around 0.7 or so, you'll have the upper surface losing laminar flow. Right? Anything less than 0.7, it has favorable gradient supporting laminar flow, so less CD. And lower surface, anything less than 0.3 will have adverse gradient, so it will lose laminar flow, and so it will have increased drag. And you can, if you draw the transition curves, you have been looking at transition curves in X-foil. So this is XTR over C, right? So this is 1 around CL of 0.3. So the same, I'm continuing the same CL scale. The upper surface, see the upper surface probably has this point around 50% chord. So at a CL of around 0.77, it will have laminar flow to 50%, and any CL less than that, it will have laminar flow to 50%. So CL less than 0.7 or so will be like this, something like this. And after 0.77, it will start going towards the leading edge. That's why, because you lose laminar flow, skin friction drag increases. Lower surface will have laminar flow till 0.33 or so, or till about 30%, or whatever this distance is. So this distance in chord wise is maybe 0.35, let's say. Then around here it will have laminar flow something like this, and below 0.3 it will lose laminar flow, so it will become like this. So in this range you have both lower surface having maximum amount of laminar flow it can, which is about 35%, and upper surface having about 50% or so, and so you have less drag. Beyond this, upper surface loses laminar flow, below this, lower surface loses laminar flow. And the nice thing is, with Profoil you can control this. If you set the alpha star of that lower surface, instead of 0.3 you set it to 0.2, this will move down. If you set this to 0.6, this will move down. But of course there's sort of laws of nature, right? You can't go and say, well, just because a method is designed to do this, I want laminar flow all the way from CL of 0 to CL of 2 or something. It just won't work. Physically it's not possible to get an airfoil like that. Likewise, if you want to decrease this CD here, one way to do that is to say, hey, if I move this point, further down and increase the amount of laminar flow on the lower surface, then instead of this I can have maybe something like this. I can move that segment endpoint to 50% chord, and then I'll get something like this. Maybe it'll lose somewhere else. Usually it's like some people call it a waterbed theory. So if you push it down in one place, it'll come up in the other place. That's just how laws of physics are. So if you say, hey, I want to improve things here, usually it'll become worse somewhere else. So a big part of this is to decide what you want. And that is itself a little bit of a design problem, right? To say this is where I want low CD. I don't mind if the CD becomes higher here. Even to know that is a part of design. But if you know that, you can do this easily with Profoil. So let's see if we can do a quick demo without getting into all the nitty-gritty details of Profile. I want to see if I can sort of show this with a quick demonstration. So I'll talk about the details of Profile and MFoil later. For now, I'll just show you with some examples. Oh, I have to. Okay, it's going to take a minute. Okay, everything is a little different on this computer, so okay, I think I got it. Okay, what I've got is a 4-segment airfoil. I don't want to get caught up in a lot of detail right now. We'll be going through all of this in pretty good detail, but right now let's just say I've got a 4-segment airfoil. Remember, the angular coordinate goes from 0 to 60, right? So quick profile demo. So we have an airfoil that looks something like this. 1, 2, 3, 4. Remember, you have to think in, at least initially, you have to think in terms of circle coordinates, and then you'll get used to it, so it's fine. So I've set this phi So phi 1 is 14.5, and this is 31 degrees, and this is 45 degrees, and this is always 60 degrees. right? Everybody remember this? So it's a kind of pseudo angular coordinates, let's say. It doesn't go from 0 to 360, it goes from 0 to 60. And so you have to divide the airfoil accordingly. So the leading edge will be around 30 degrees, we've called it 31. And this is around 45 degrees, this is around 14.5 degrees. And I've set the alpha star for this segment as 7 degrees and for this segment at 3 degrees. And I'm plotting, so what I've asked Profile to do I'm making Profile design an airfoil shape with alpha star of 2 equals 7 degrees, alpha star of 3 equals 3 degrees, and plotting so Profile can design the airfoil and it will also plot the inviscid velocity distribution. So Profile it's really an inviscid design code. So if you want viscous effects, you have to take that airfoil, run it in Xfoil and see how it looks. So anybody know how I can, are you able to read this? Okay, so again, without getting into details, these 4 foil lines tell Profile what the segment endpoint is, where it is in angular coordinates. So these 4 numbers, 14.5, 31, 45, 60, these give the angular coordinates of the segment endpoints 1, 2, 3, 4. These give the alpha stars. So first and second segment have alpha star of 7, third and fourth have alpha star of 3. We'll just ignore all of these lines, we'll ignore all of these lines for now, and then we'll just talk about these just very briefly. So essentially I give these specifications and then I tell Profile go design this airfoil, and then I tell it go run this airfoil at an inviscid, or give me the inviscid velocity distributions at these 5 absolute angles of attack. So alpha z of 0, 3, 5, 7, 9. Well, let's make this 1 so that it will be evenly spaced. 1, 3, 5, 7, 9. So here I should not say 0. So 1, 3, 5, 7, 9. Okay, so that's what I'm telling Profile to do. Let me save this. Wait, am I saving it in the correct place? No, I should save it in. Okay, now, and we're going to use an MATLAB interface called mfoil, which is what, and you'll be doing all this, but right now I don't want to get into details of how to run it. So let me just do a couple of things. Okay, so when you run it, if it runs successfully, it will plot the velocity distribution here, it will plot the geometry here, and then it will plot alpha stars here. We'll ignore this window for now. Let's just focus on this. So it took all the specifications I gave it and it designed the airfoil. So this is the airfoil that it came up with. So think about it. You didn't even think about how the airfoil should look and all that. You were thinking about how the velocity distribution should look. And these are the inviscid velocity distributions for those 5 angles that you asked it to do. So absolute angle of 1 degree, 3, 5, 7, 9. So 1, 3, 5, 7, 9 on the upper surface, and these will be 1, 3, 5, 7, 9 on the lower surface. Now look at the velocity distribution at 3 degrees. on the lower surface, which is this segment, this velocity distribution is exactly constant, or at 3 degrees. At anything less than 3 degrees, it's adverse. At anything greater than 3 degrees, it is favorable. That's because that's the rule for the lower surface, right? At 7 degrees, so this is 1, 3, 5, 7. So this is 7 degrees. 7 degrees, the upper surface, this segment has got 0 velocity gradient. Greater than 7, it will have adverse. Lower than 7, it has favorable. And look at the shape. The shape, it's not like it's horizontal or something. So the shape, it's very, very hard to think of what the shape should be to get a certain velocity distribution. If you had to go and manipulate the shape, I mean, you would just struggle for a long time. Whereas with an inverse design, you can say, I want this velocity distribution, just go figure out what the shape should be. Now, if you want to redesign this airfoil, okay, let me call this, I'm going to save this airfoil as some demo1.in. I'm going to save this. And now I'm going to change it. Instead of 7, I'll change the second segment to be 5. So what do you think will happen if I run this? Second segment alpha star is now 5. Come on, you know what will happen. Yeah, now this velocity distribution at 5, it's favorable, right? That should become horizontal. 7 will become adverse, and who knows what the airfoil will be like. We don't know. So let's run it and see. Okay, so when you're designing these things, it's always nice to have the previous iteration also shown. So the previous iteration is shown as a white dashed line, and the current iteration, the current airfoil, is shown as a green line. And so is the geometry. So this was the previous geometry, this is a new geometry. So one thing you can see is at 5 degrees now you have 0 velocity gradient. At 7 it has become adverse. But we didn't change anything about the lower surface. That is still maintained. At 3 degrees it has 0 velocity gradient. And this is what it says the shape should be to satisfy that whatever new specs you have put. And it figured out that it has to move the lower surface to here. I mean, normally you wouldn't think of it like that if you're doing it with geometry, right? You'll go change the upper surface. You'll think that will affect only the upper surface velocity distribution. But it turns out they're all coupled. So this thing has figured out that it has to move the lower move the lower surface in order to keep the lower surface alpha star the same, and the upper surface has to be like this. Okay, so let's call this airfoil demo 2 or something. Now let's go back to the original one and say I want laminar flow on the lower surface or something to a larger distance. Okay, so I'm going to go back to this and change this back to 7, and we'll run this so that we sort of get that airfoil back there. So now this is the green is now the current airfoil, the thinner airfoil that we had earlier is white. So if I run this again, it'll just sort of clean it up. So now we have this airfoil, right? This is demo 1. Now let's say we want, let's say we want to extend this more down to increase the amount of laminar flow on this, something like that. Let's say that was the objective. I can go and say, instead of 14.5, what do I have to make it? This is the phi, the angular coordinate of the first segment, and that's what this is, right? That's what this is, this point. I want to move this here somewhere. Do I have to increase it or decrease it? Decrease it, right? Then it will move closer to the trailing edge. Let's make it 10. And now I go and run it. So now that's what's happened. I moved this point from 14, phi of 14 to phi of 10. And it decided that it has to make this shape like this. And look at this. This is still 7 degrees. 7 degrees alpha, absolute alpha. This has got exactly 0 pressure gradient. The level has changed. The velocity level has changed. That's not controlled by alpha star. But the gradient is 0. And it had to do something with the lower surface, right? It had to figure out that the lower surface has to go like this and upper surface has to go like this, and it sort of did all that by itself. And because of certain things we specified with the pitching moment, which I have not talked about, it actually creates a little negative lift in the bottom or in the trailing edge, and it created a slight reflex here. So I can usually zoom in and say, okay, this has got a little reflex here. That's because of the way I said keep the pitching moment at some value, and we haven't talked about that yet. Okay, so this is just a sort of illustration of how this method is really, it can give you things that are very non-intuitive, but it can give it to you very easily. So now let's talk about, let's stop the demo part and talk about how all the file structure is and what you have to do, all the more sort of bookkeeping things. So the codes we are dealing with here are Profoil and MFoil. So Profoil is the actual inverse design code. It's written in Fortran. And I'm going to give you an executable for Windows, which is why I mentioned in the syllabus that this part you will need Windows, or if you use a Mac, I think there's a Windows emulator that you can download or something like that, right? So I think some people have figured it out, and I can pass on some maybe tips on how to do that if there's interest. MFoil is a MATLAB GUI, which is graphical user interface. So this is a sort of a wrapper that goes and runs Profoil, and it plots all the information, and it even helps you to graphically go and edit certain things, which we'll see later on. So it turned out Professor Michael Selig, right, my PhD advisor at Illinois, he wrote the Profoil code, and he was working with it just with the file structure without using I mean, he had some plotting tools, but when I started using it during my PhD, I found that really hard to use, and I wrote this MATLAB GUI. And then I think now everybody is using it. Everybody who's using Profoil is using it through this MFoil. But it's also, I mean, I wrote MFoil, maybe the last version I wrote was in 99 or something, 98, 99. I really haven't updated it since I've come here. So although it makes things so much easier, it's about 20 years old. No, maybe not 20, 18 years old. So some things are a little clunky, and I mean, I've not had time to change it. I don't, you know, I'm able to work with it because I'm used to it, but maybe sometimes somebody should change it a little bit. So that's what Profoil and MFoil are. When you download it, you will have this directory structure. It'll automatically, the zip file, if you extract it, will create this directory structure. and you need to keep it pretty much like this, otherwise there's a chance that you will break it, right? And then there may be other directories which you could create, but so you download mfoil and it will create these 4 important directories or folders. Don't go and alter it, okay? The MATLAB interface assumes that this is the structure. If you go alter it, then the MATLAB interface won't work. This is my 2-minute alarm. Okay, so this is the working directory. This is where profile.exe is. This is the executable. This is where the profile executable is, and this is where the MATLAB files are. So MATLAB files are here. And this has got all the saved profile input files. So when you download this directory, so you will have this directory called mfoil, the parent directory with all this structure, right? You can put this wherever you want in your own PC or laptop, but put it in a place where the upstream structure that does not have a space in the name. So in other words, so this mfoil parent directory, right, the main directory, so put that in a folder where so in other words, don't put it like here. So you'll have C:\program files, backslash, you might have all kinds of things, and then you put mfoil, right? Now, so remember, this is what I mean by saying this is about 20 years old. At that time, Windows did not create these things called program space files. People would, almost all the time, people would write directory names without spaces. So now there's a space here. And I think sometime I should find the time to go and change mfoil so that this is not a restriction, but it's like there's no time to do anything these days. Space here creates problems. And just to finish this thought, instead you should put it here. Like you can put it in C:\documents or something, \mfoil, or just put it in C:\mfoil or something like that. Anything where there is no space in the directory structure. So a good way to find out is once you put it here, go to MATLAB and say pwd, print working directory, or just go to command line, command window and go to this and make sure there's no space. Okay, we'll stop here. In the next class, we'll talk about how to run xfoil or mfoil.